Hello everyone, welcome back to another video. Today's video is a submission for the Summer Math Exposition 3. If you'd like to learn more about it or watch the other videos that were made as a part of this contest, please feel free to click the link in the description or click on the playlist I linked in the end cards. Today I'll be going over the following challenge problem. Suppose a fair coin is flipped repeatedly. How many flips would you expect to have to make before your previous 2012 flips are this alternating sequence of heads and tails? So heads, tails, over and over and over for 2012 separate flips. Oh, and to be clear, I will be using H to denote heads and T to denote tails for this problem. I'll give you a couple seconds to think about it, and when you're ready, resume the video and I will show the solution. Okay, for this problem, I'm actually not going to solve for this specific case of 2012. Instead, I'm going to use a trick where I first generalize the problem to all positive integers, even integers for this number, because we do need this heads, tails thing to have an equal number of heads and tails. And then I will just plug in our 2012 number here into the generalized formula. But to start off, we're going to generalize this problem. So instead of saying 2012 flips, we're just going to say 2n flips, which is, of course, the generalized form here, because we do need an even integer number of flips. And instead of considering 2012 flips here, I'm actually going to reword this to be 1006 pairs of heads and tails. And the rationale behind this will be apparent in a bit. But of course, we're working with a generalized case, so instead of 1006, we will use n. Now, to solve this problem, I'm going to define a function that solves the problem for us, and then find a way to find values for that function. Okay, so the function we use is not actually going to be the exact answer. It will be off by a little bit, but I'll show why this is actually a better function to use than just the function that gives us the answer to the problem. So, we're going to define our function, right? F of x, or I guess f of n in this case, f of n, as the following. F of n is the expected number of flips after the first to get our HT combination here, which of course has n pairs. Given that the first flip is heads. Now, the reason why I'm defining this in such a complex way instead of just writing it as the expected number of flips to get this sequence will be apparent in just a bit. So to find the exact formula for f of m, I'm going to use a method known as recursion. And if you've done proof by induction before, this will be a very similar process. So to start off, I'm actually not yet going to solve for f of 1. I'm just going to say that f of 1 is equal to some number p, because, well, this equation will always give us some integer, so we'll just call it p for now. And we'll come back to it in a bit. Now, I'm going to assume that I already know the value for f of n minus 1. So it doesn't matter what it is right now, we're just going to assume we know what this number is. Now we're going to solve for f of n. Now how do we solve for f of n? Well, consider the case where we have successfully gotten n pairs of these HTs in our very long sequence. So we can imagine that the sequence goes something like, we'll start with like h. So for all these problems, we're actually going to assume we're starting with h, and then we will expand on what happens if we start with t later on. You can imagine it starts with h, we have a lot of flips, and then at some point we have HT, and we have met our requirement of n pairs of these. Well, for this to happen, we must first have gotten n minus 1 pairs of HTs, right? Because we can see if we just cut off this last HT, this is just n minus 1 pairs of HTs. So before we get our final state, we have to first reach this n minus 1 state. However, not every time, it's not necessarily the case that every time we reach the n minus 1 state, we will also reach the end state. Consider a set of flips that have reached the n minus 1 state. So the state would be here, and here there would be n minus 1 pairs. Now let's look at the next two flips. For this to be a successful, sequence, these two have to be heads and tails respectively. Anything else, and we might as well have never gotten this in the first place, because we'll have to start over. In fact, there are 4 separate possibilities for these two, and I'll write them down here. So we could get HH, so 2 heads, HT, TH, or TT. We know in the case of HT we are done, and so here I'm just going to write done. And we know in every other case we're going to have to essentially start over. And in fact, I'm going to just draw this line here to really emphasize that. If we don't succeed, it's as if we never had this. We could have just been starting once again from the second flip. And the reason it's the second flip is because, remember, we're imagining that the first flip is always this H, and it's immutable. So let's consider these two cases first. And it's because both of these cases end in an H. And in fact, because they both end in an H, they will have the exact same effect on how long it should take us to get another set of these. And in fact, by definition of f of n, it will take us exactly f of n, n minus 1 more flips to get another sequence of length n minus 1. As for tails tails, this one is a little more complicated. However, we don't need to make a new function for tails specifically. In fact, consider what happens if we have tails and then we start over. Well, if we get a heads at any point in this, like let's say we get a few tails, then we get another heads, we can just set the cutoff line there and start over and just add however many are in here to our resultant number. So we know this is f of n minus 1 plus something, but we're not sure what it is. Now, to solve for that is actually pretty simple. Consider something like this, where we don't have any flips beforehand. Actually, I'm going to write this on the other board. Consider a case where we have nothing beforehand. There's no context, we're just flipping a coin. How long would you expect it would take before we get a tails? Well, we can use the fact that there's a 1 in 2 chance of getting tails, and say that it should take us 2 flips to get a tails on average. Of course, to get a heads. That's my bad. I meant to say heads. Get a heads on average. Of course, you get a heads on the first one, the second one, or the third one, but on average, it will take 2 flips. Now, we should, however, prove this empirically, and here's how we're going to do it. The probability of the first flip being the first heads is, of course, 1 in 2, and we'll multiply that by 1, since that is the length of our string that we'll have until we reach a heads. The probability of it being in the second one is 1 over 2 times 1 over 2. And the reason for this is because if the first head was already here, then no matter what happens in the second heads, it won't be the first heads, right? So that means that this would be 1 in 4 times 2. And the same logic applies to every single flip afterward. So we'll get 1 in 8 times 3, 1 in 16 times 4, and this infinite sequence, that's just 1 in 2 to the n times, actually I'll use a different q times q. Right, and it goes on forever. Now this might seem a bit complicated to solve, right? Because this isn't some easy geometric sequence. We got all these messy, we kind of this arithmetic sequence mixed in with a geometric sequence, to my stomach it's going to be very difficult to find an answer to. However, it's actually not, and here's why. Let's draw out all these numbers, and instead of multiplying them by 2, I'm just going to add them repeatedly, which is, of course, the definition of multiplication. So we'll start off by writing 1/2 here. Then I'll write the 2 1/4 beneath it, the 3 1/8 beneath it, and the 4 1/16 beneath it. And we just keep going in every column, and there's an infinite number of columns. Let's look at this first column here. We're summing 1/2 plus 1/4 plus 1/8 plus 16. Now, you might remember this is equal to 1. But specifically, we can use this formula, a over 1 minus r, for an infinite sequence, where a is our first term and r is the ratio between these geometric terms. And for this one, we'll get 1. For the second one, we don't actually need to use this formula. We see that the second one, the second long infinite series, is just equal to the first one minus 1/2. So this will be 1/2. And this third one is simply equal to the second one minus 1/4. So this will be 1/4. And this will go on and on forever, giving us this geometric sequence. Now we can again use the exact same equation to solve this geometric sequence, and that will give us an answer of 2, which tells us that on average it should take 2 flips to get a heads, just like our intuition told us earlier. So now that we know this, the only difference between starting with the tails and starting with the heads will be to add 2 to the number of times it will take to get this sequence again. And we're almost there. Now, if we ever reach this, in this table below, if we ever reach this done state, we know that we're done. Which means we have successfully gotten our n pairs, and however many flips we've gone before then will be our f of n. However, what we're really doing here is rolling a 4-sided die and picking one of these options, right? They all have equal probability. And so the question is, on average, how long will it take to get this done state? Well, we can do the exact same thing we just did. If we consider each pair of these after this long sequence as one dice roll, with probability 1/4 of succeeding, we can see exactly how many of these it's going to take before we successfully reach our done state here. How do we do this? Well, consider the first time we reach this state. There's of course a 1 in 4 chance of getting this done state. And since we're counting the number of times we need to reach this state, this n-1 state, before we reach the end state, we're just going to go ahead and multiply that by 1. Similarly, the second time has a 3 in 4 chance of even getting here, because if we succeeded on the first time, we would not even get to the second time. And a 1 in 4 chance of succeeding on the second time. And similarly, we have a 3 in 4 times 3 in 4 times 1 in 4 chance for the third time, and so on. This might look familiar. It's another one of these infinite geometric sequences with this arithmetic sequence hidden in between. And we do actually just solve it the same way. So we'll write 1/4 up top, and then I'll simplify this to 3/16. 3/16. That one becomes 9/64, 9/64, 64, and 27/256, 27/256, 27/256, 27/256. And of course these go on infinitely. And now we add them all together. And this is where our equation, a over 1 minus r, really comes into effect. You probably don't know what this adds up to on top of your head. I know I don't. And this is where this comes into use. We see that our common ratio is, of course, 3/4, and so our first term is 1/4, so if we plug that in, 1/4 over 1 minus 3/4, that simply goes to 1/4, so that's just equal to 1. So our first thing adds up to 1. The second one is, of course, just the first one minus 1/4, so that is 3 over 4. The next one is just 3 over 4 minus 3 over 16. This one's a little harder to calculate, but it should go to 9 over 16. And in general, this is always times 3/4. And if we use the formula we just used up here, we will get 1 over 1 minus 3/4. That becomes 4. So, as our intuition might tell us, it should take us 4 separate, on average, we'll have to reach the state 4 times before we successfully reach the f of n state. Okay, but we're still running into the problem where we also have this tails-tails state, which isn't the same as the other two. It actually will not be a problem. Because we expect to take 4 separate rolls to reach this state, and each state comes with equal probability, we can also say that we expect to hit each state exactly once. Now, even if we succeed on this first try, we'll still need to hit the state once. And so, always, we'll have to add f of n minus 1. But it's even worse than that, because not only do we have to hit f of n minus 1, we also have to add these two. So we'll actually have to add 2 here. Then, on average, we should hit each one of these states once. So we can actually just add them all on, and remember to add 2 to each one of them, because the way we're counting it, we're actually forgetting to count these two. So we're compensating here by adding 2 to each one. And simplifying, we get f of n equals 4 times f of n minus 1 plus 10. And we're so close. This is so close to our actual answer. We now have a recursive formula for the function that almost answers our question. And this is where this definition comes in. F of 1 equals p. So I'm going to start writing down the the smaller values for f of n. So f of 1 we've known to define as p, and by definition of f of n above, f of 2 will be 4p plus 10. F of 3 will be equal to 4 times 4p plus 10 plus 10, which I will rewrite as 16p plus 40 plus 10. And the reason I'm writing it like this, we'll be comparing in a second. F of 4 is just 4 times 16p plus 40 plus 10, which is equal to 64p plus 160 plus 40 plus 10. And you might see the pattern here. F of n is equal to 4 to the n minus 1, because f of 1 is this, times p, plus this infinite sequence, which goes 10, 40, 160, etc., 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 all the way up to 4n minus 2 times 10. And here is where another equation will help us out. If we go ahead and factor 10 out of this equation, we have an infinite exponential that starts with 1. And luckily there's actually a very nice equation that helps us deal with these. It is 1 minus r to the n plus 1, or I guess we'll call it k here, k plus 1 over 1 minus r. And k here is just our largest exponential. So plugging this equation in, we get 1 minus 4 to the n minus 1, because n minus 2 plus 1 is n minus 1, all over 1 minus 4, which simplifies to 4 to the n minus 1 over 3. And there we have it. F of n equals 4 to the n minus 1p plus 10 times 4 to the n minus 1 over 3. But remember, this is only the solution for if we A, pretend that the first flip doesn't count towards our total, and B, pretend that the first flip is heads. Well, the remedy for pretending that the first flip doesn't count towards our total, we'll just add 1, because now we counted the first flip. But we do need to account for what happens if we start with the tails. But we can actually use a very, very similar trick to what we did here. We know on average it takes 2 more flips after the first tails to return back to heads. And once we get to heads, we know that it will just take this many flips for us to get to our special case. So to account for the tails case, we need to add 2 whenever it's a tails. However, tails only comes up half the time. So instead, we will add 1/2 times 2, which of course simplifies to 1. And this changes f of n from this definition to a different function. We'll call it g of n. And this will give us our real answer. So g of n is defined as 4n minus 1p plus 10 times 4n minus 1 minus 1 over 3 plus 2. And we'll go back to our specific case. Our specific case considers 2n equals 2012, so n equals 1006. Plugging in 1006 into this equation gives us 4 to the 1005p plus 10 times 4n minus, 4 to the 105 minus 1 over 3 plus 2. And we're so close. This is almost a complete solution. We are missing one key part. What is p? Now, remember, we defined f of 1 to be equal to p. So let's consider the case where we have h, and we want to see how long it takes us to get a heads tails. But if we already have an h, then that will just be our first occurrence of a tails. And we've already solved this problem. It should take us 2 more flips. So p is actually just going to be equal to 2. And thus, our answer is, and actually I'm going to simplify these powers to powers of 2. So 2 to the 2010 times 2 is 2 to the 2011, plus 10, I will take 10 into the numerator, 5 times 2 to the 2011, since 10 has a factor of 2 in it, minus 10 over 3, and this 2 becomes 6 over 3. And if we quickly simplified it, you can try to do it on your own, we'll get an answer of 2 to the 2014 minus 4 all over 3. And that is the expected number of flips it will take us to get this monstrous sequence of 2012 flips anywhere in our sequence of flips. Thank you for watching, I hope you enjoyed, and if you did, please consider subscribing to the channel and liking the video, and I will see you next time.